Hello everybody, how are you? Nice to see you. And we're going to be talking about a math competition that was organized by students now. So this is the Mustang Math Tournament, and it always is really interesting to talk about competitions which are run by students because, you know, one of the hardest things to do is to make problems. And when you go through the act of actually making the problems yourself, you often find lots of very interesting insights. So hats off to the people who made this competition, even though I don't have a hat on. I don't know why I did that. But in any case, let's go ahead and start talking about some of these problems. Okay, and I want to emphasize that this is an official collaboration with Mustang Math Tournament. We're very happy to work with all of them on this. Okay, and maybe at some point I'll get a hat. So, okay, let's continue and start doing some of these questions. The way that always I do these things is that I don't actually do the problems before I see them. My team goes and picks some interesting questions to think about, and that's on purpose because that way you'll get to see how I go about looking at something for the first time and trying to figure out what to do. Let's do this. Question Relay Rodeo number 10. A flower is made by attaching the smallest... Attaching? Yeah, okay. The smallest prime factor of 160. Oh, that's what the bracket means. Okay, it's that many circular petals, whatever is the smallest prime factor of 165, of radius 1 meter to its stem of negligible radius, such that the petals are parallel to the ground and the petals may overlap. Okay, I get it. If the maximum surface area of petals that is exposed to the sun, the area visible when observing from a top-down view, can be expressed in simplest form as a pi plus b times the square root of c divided by d. What is a plus b plus c plus d? Okay. Well, first we need to know what is the smallest prime factor of 165. Oh, neat. When I look at this, I just immediately saw that 1 and 5, like 1 plus 5 equals 6. That means that this is 15 times 11. Okay, the multiply by 11 you can do with a 2-digit number by pulling them apart and put the sum in the middle. Okay, that's nice. That means that the smallest prime factor is 3. Okay, right. So this is 3 times 5 times 11. And so now we know that there are 3 petals of radius 1 meter attached to the stem of negligible radius. And now we want to have like the maximum possible surface area. Oh, this is hard. You want me to draw circles? I mean, 1 circle is quasi-okay to draw. But if I need to draw 3 circles, that's going to be painful. So the way I'm thinking of them is that these circles are all, I guess, centered here somehow. That was supposed to be a bottom. Oh no, how in the world do you do this? This is really hard. It's really hard to draw the circles. Oh, it's like a Venn diagram. Sort of. Okay, this is like sort of 3 circles, okay? So I guess I should have just drawn a Venn diagram and that would have been good enough. But these are supposed to be 3 circles and each of those has radius 1 meter. And I want to know what is the surface area that I managed to make. All right, so that means that each of these is radius 1. And so what I see is that the answer is going to be just... So what I have to do is I have to take 3 circles and I minus the stuff that I overcounted. And in fact, I overcount each of these overlapping things. I double count each of these overlapping things. So my total answer for the area is going to be pi r squared, which is 3 times pi r squared. That's 3 pi is the area of the circles. This is in meters, right? I assume this is in meters. Okay, so 3 pi is the area of the circles, and I need to subtract off exactly 1 of each of these things. And the reason I only have to subtract off 1 of each of these things is because it's because of the fact that I double count each one. So each one is counted twice, and there's 3 of them. All right, you all know I'm pretty lazy. Is there an easy way to do this? I guess the way I see this is a fairly standard type of thing to do. So if I went and grabbed one of these guys, let's call that a circle. The nice thing is that we've got like 60-degree angles here. This is supposed to be an equilateral triangle, just kind of mashed on the side. But I have this one, and this is 60 degrees. And what I'd like to do is I'd like to just look at that little bit over here. And I want to subtract off 6 of those things. right? Because I'm going to take the 3 big circles minus the stuff that is double counted, and there's 6 of these little half things. So I need to do this thing, and I need to do 6 of these things. So I'll take this first thing, and then I'll minus 6 times these like wedge things. And that's going to be my answer. So how do I find the wedge thing? Well, the way you do that is you go and find the area of the sector of the circle, which is 1/6 of the pi, because it's pi r squared, r is 1. So it's 1/6 of the entire circle. All right, and then I subtract off this little equilateral triangle. That's equal to, well, this is like 1, and then this little bit is 1/2, and this is 1/2 root 3, because that's a 30, 60, 90. Let's just write that. Okay, that was supposed to be a right angle, sort of. Okay, so this thing here is 1/2, and this thing here is 1/2 root 3. So half base times height, that's half the base right there. So that's 1/4 root 3. Root 3 over 4. That's this little piece. Okay, we're almost done. We need to do 3 pi minus 6 of those. Oh, look at that. 6 times 1/6 pi is 6. So then what I end up getting is I end up getting 2 pi. That's because that's 3 pi minus 6 times 1/6 pi. Okay, minus, and the minus gives you a plus. Plus, so this is 6 root 3 over 4. That is 3 root 3 over 2. And that is exactly the format that I wanted. I have A, B, C, and D. Add them all up. So the answer is going to be 2 plus 3 plus 3 plus 2. Oh, that's symmetric. 2 plus 3 is 5. 3 plus 2 is 5. 5 plus 5 is 10. Is it 10? Let's find out. It's 10. Oh, and it's question number 10. I bet they did that on purpose. Next question. What is this? This looks like a horse thing. Yeah, it's a horse thing. Okay. What is the number of ways to complete the relay rodeo problems up to and including number 10? See round graph below, such that you complete the prerequisites of a problem before solving the problem. Whoa. Okay, I apologize to the people who are watching on YouTube. It might be kind of hard for you to read this, but I'm going to try to highlight the important parts, okay? What is the number of ways to complete the ones up to and including number 10 such that you complete the prerequisites of a problem before solving the problem? Okay. Let me try to rewrite this in a way that you can maybe see online. Or will that help? Quick question. Can you guys actually read the numbers here? If you can, that's good, because then I don't need to redraw this. So if you, I guess, go into like, I don't know if you can go into 1080p mode or something. Hopefully you can read these numbers. Oh, good. I see a lot of yeses. If you can't see it, that means you should just change your settings to be like higher resolution, and then you should be able to see it. Because some people said they can. So I'm just going to tell you what they are. Like, that's a 1. That thing here is a 2. This thing here is a 7, and so on. Okay, and now it's saying that I need to know how many ways can I complete them. So the answer is not 10 factorial. I can't do them in any order that I want. Is there a nice systematic way to do this? You can see I'm thinking this through. I'm like, how should I try to do this? So I like to often try to reduce the problem to an easier problem. But in this case, I see a bunch of different paths that I can take at the same time. It's tricky because some of these go back to each other. So some of these paths go back to each other. you can see that when I see a question I don't know how to do, I'm thinking through like, how can I simplify this, right? The way I'm looking at this is like, I have to do number 1 first, but that doesn't help me very much because after that, then I have a bunch of choices that I can use. So if we look at this, we can try to draw this in a nicer way, right? So I'm just trying to look, it's in the shape of a horse right now. But I see like there's 1 at the top. And then I have a bunch of paths that go down. So 1 goes to 4. The numbers are actually not super important what they are. Then there's a 5. And then here's this like 10. Random 10 is just sticking out, okay? But then there's this 9. And then the other way is I can go 1 goes to 3, goes to 6, goes to 9. And then there's also 1 goes to 2, goes to 7. 7 goes to 9, but it also can go out to 8. Oh, it's symmetric. That's nice. Okay. So I just found out that it's this nice symmetric picture in the sense that it starts there and I've got these parallel things I can go to and then out to there. 1 has to be the first, right? So I can simplify the problem first by saying 1 has to be the first no matter what. So I just need to know how many ways are there to go through all of these. I've just made the problem very marginally easier. So now if that's the situation, I see that various people are like, commenting with ideas. That's cool. So it's like now I have a bunch of choices, right? I have to say who's next. The next person is either 2, 3, or 4. And actually, if it's 2 versus it being 4, the number of ways to finish is actually going to be exactly the same. The reason is because once I take away a number, if I took away the 2, the picture looks exactly the same shape as if I took away the 4. So the answer to this is going to be a bunch of things added together. All right, let's try this out. Oh, the picture is back. But I actually wanted more space. Let me go backwards the screen. There'll be a lot of space there. Okay? So the answer is going to be, there was a 2, a 3, and a 4. So there was a 4. Well, let me write it this way. The answer is going to be 2 times the answer if I went and picked off the 2 first. Because if I pick off the 4 first, the answer is just going to be the same as picking off the 2 first. That's the same number of ways to finish. So I'll say that the answer is going to be 2 times the number of ways to finish. What happens if I did, took off the 2? So 4 and a 3, 5 and a 6. There's a 7. Now all of these go in here into 9. Then there's an 8 and a 10. Okay, so it's this thing, plus the number of ways if I just took the 3 out first. That's the middle one. And if I took the middle one out first, I would get 4 goes to 5, goes to 10, and I have a 6 goes to a 9, this goes to a 9, this comes from a 7, this goes to an 8, and this was a 2. Do I really want to do this? Do I really want to do it this way? So as I look at this, this is also not very much fun. So, I mean, what I was showing is I can sort of take the problem and I can take bits off of it at a time and I get some sub-problems that I can try to solve instead. Is that any better? Is there a better way to do this? Oh, actually, so here's something else I can think of. If I look at this, I sort of have 3 parallel chains. Oh, that's interesting. Is that the way to think of this? When I said I have 3 parallel chains, it's like if I didn't have them intersecting with each other, then I would sort of just be talking about interleaving 3 chains with each other, which would have some more hope of being solved. But now, what actually happens is that this 9 thing matters in the sense that as I interleave these chains, Maybe that's the way to go. Let's try this. Okay, let's try this. So I'm going to start by, I'm going to throw away what I did over here. This is no fun. This is awful. If I go back here, more space. Very good. So I have this 3, 6, 9. And let's think of them going into some order, right? And I'm going to write them in a different pattern now. I'm going to say I have a 3 going to a 6, going to a 9, okay? And then there was a 4, 5, 10. 4, 5, it went to the 9, and it also went to the 10, okay? And then there was the 2, 7, 8. 2, 7, 8, but by the way, 7 also went to 9. So what I'm thinking about here is I'm trying to make an ordering. I know that 1's in the front, that's why I got rid of the 1. But now I have the 3, 6, and 9. So let's just put the 3, 6, and 9 down first. 3, 6, and 9. So now once I've put this 3, 6, and 9 down, let's just see how I can put the rest in. So I have this 4 and 5 and 10. How is that going to work? So I'm allowed to put the 4 and the 5 and the 10 where all that matters is the 10 goes after the 5. See, I'm thinking of like interleaving. It's almost like it's like a shuffle, except that I don't need to put the 4, 5, and I don't need to put like 4 and 5 like this, and then like the 10 like that. I just need to make sure the 4 and the 5 live on that side, and then the 10 lives somewhere after the 4 and the 5. And then the last part will be I have to interleave those pieces in there too. Okay. How many ways can I do this? So, you see, the way I'm thinking of it is I'm just trying to see how can I put the 4 and the 5 down. And at first, maybe I won't find that systematic of a way, and then maybe it'll get nicer. But if I want to put the 4 and the 5 down in this part, that's almost like a stars and bars type thing, where I have, some gaps that I can put numbers, and I'm going to put a 4 and a 5. But the reason why that's still a little bit annoying is that where I can put the 10 is going to how many choices I have for the 10 is going to depend on the 4 and the 5 location. Is that true? Yeah, that is true. So, this is still not very nice, because you see, the way I'm thinking about this is like, let's pretend that I actually went and started putting them down. Suppose I went and put a 4 here, and then a 5 there, and then I put a 10 there. Okay? I'm just thinking through like, how would I finish the problem? If I put those things down, suppose they went there, now I have to put a 2, 7, and 8 down. And the 2, 7, and the 8, where they go down, like how many choices I have for them to go down, it's going to depend in some sense on how many numbers there are to the left of the 9. That's actually what's going on here. I suppose that's not that bad. Okay, let's try this. Let's try this. This is a pretty interesting question. Yeah, what's going to matter is how many numbers are to the left of the 9, and I actually have really only 2 kinds of possibilities, which is based on where the 10 goes. Let's try this. Okay, so I'm going to do something that's at first going to look a little bit more case-ish, but maybe we'll notice something from it. So if I put a 4 and a 5, both B4, right? The way I see it is that I have like this area and that area and that area. That's where I'm going to put the 4 and the 5. So either they both sit there. If they both sit there, I've got lots of places the 10 can go. Oh, the 10 is going to be called an X, okay? That way I don't have to worry about 2-digit numbers, okay? So I have a 4 and a 5 and a 10. That's one possibility. Or I have a 4 and a 5 and the 10 goes here. Or a 4 and a 5 and a 10 goes there. Or a 4 and a 5 and a 10 goes there. Those are all the possibilities for having the 4 and the 5 both live in that spot. Okay. Now, interesting thing is I'm going to consider that guy to be different from the previous ones, because that guy has the 10 after the 9. I think that's actually what's going to be relevant. So that one's going to come out to be, that's a 4 and a 5, different color, I'll put a 10 at the end. Okay. Now I've got more possibilities. I can also, instead of putting 4 and 5 both there, I can put just the 4 there and the 5 in the next one. It could be 4 here, and then the 5 could be here, but the 10 has to come after the 5, so it'd be like this. Or it could be 4 here, and the 5 there, and the 10 comes next, in the next spot, sorry, the next segment. Or I can have the 4, and the 5, and the 10's in the last spot, meaning after the 9. Okay? Next thing, that's like if the 4 is here and the 5 is there. I can also have the 4 here and the 5 be in the last spot before the 9. 4. 5 is in the last spot before the 9. That would be if the 10 is also before the 9. And the other one is a 4 here, a 5 here, and the 10 is after the 9. All right. Now, what happens next? The next thing that I can have is I can have I already dealt with all the possibilities of a 4 being inside this spot. You see, I'm basically saying there's a 4 and there's a 5, and I've got some places that they can sit. The next one would be, I've done all the possibilities where the 4 is before the 3. The next one is where the 4 is after the 3. So I can have the 4 and the 5 both after the 3. And also the 10. Or I can have the 4 and the 5 both after the 3, the 10 next. Or I can have the 4 and the 5 after the 3, and the 10 after the 9. Okay, I guess I can keep going. The next thing is I can have the 4 here and the 5 in the next one. And the 10 is there. Or I can have the 4 here, the 5 here, and the 10 is at the end. So far, I think I've dealt with all the cases of if the 4 is in this piece, the 5 is either with it or after it. Don't share the answer yet. I'm actually trying to go and think through it. I'm trying to think through this, right? And the point is, the 4 can also come after the 3. Yep, we're doing that right here. And I'm also doing this slowly because I sort of want to show like there's some nice patterns that are coming up. So this was the case where the 4 is here, and then the 5 is in the next spot, and then the 10 is either with the 5 or afterwards. The next possibilities have the 4 and the 5 both here, and it's either 4, 5x or 4, 5 and the white x. Okay? Good, I see it. So I ran out of space, so I'm going to put it up here. 4, 5x, or 4 and then 5. Let's put them both here. 4 and then 5 and then x. Now, why did I do that? I did this because the idea is, I think that the question for when I put the 2, 7, and 8 down is just only going to care about how many numbers there are before the 9, because that's somehow going to depend, that's going to somehow decide where the 8 is going to go. How many choices I have for the 8. The 8's this free thing that can do whatever it wants to. So what I'm saying is that after the first 2 rows are done, I'm going to have 6 numbers down. There will be 6 numbers down, and these 6 numbers that are down, well, I'll either have 9 at the end, or I'll have 9 right before the end. Those are the only 2 possibilities. Either the 9 comes before the 10 or the 9 comes after the 10. Okay? So in that case, let me see. If I go back one, do I have more space? I do. How come I have so much space as I'm going back? I don't understand. But let's just keep going back another page. And I'll go back another page. I want to count this up first. How many options had the blue? 1, 2, 3, 4, 5, 6, 7, 8. Wait, I can't count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 blues, okay? So there's 10 blues. And how many whites? 1, 2, 3, 4, 5, 6 whites. And white means that you have 9 and then a 10. And the blue means that you have 9 at the end. If that makes sense. These are the 2 different possibilities that we have here. Okay? And hopefully we counted that right. Why is there a random squiggle here? Don't know. Okay. So hopefully we counted that right. We got 16 so far. Do I believe 16? I'm just doing a quick thinking. Yeah, it seems reasonable. 1, 2, 3, 4, 5, 6. Okay, so I've got this. All right. So now let's see. So if I've gotten all of this, the next thing is right. So we're here, and the next thing that we can do with this is now we want to go and I guess analyze those 2 cases. So what if I have the 6 numbers and 9 is at the very end? So if I have these 6 numbers and 9 is going to be the last number, if I have 9 here, and then of the other things I've got 1, 2, 3, 4, 5. I've got these numbers. These are all my numbers in here. And now I'm supposed to slot in the numbers 2, 7, and 8. And the only rule is that to the left of 9, you're supposed to have both 2 and 7. And 8 is after 7. Okay. How to do this? Okay, so I need to have 8 be after 7. I'm just thinking about this, if there's an easier way to do this. Because I'm trying to put this into like a stars and bars type situation where I just need that there's at least 2 of my numbers out here. Okay. I suppose I'm doing, okay. So if I want to know how many ways I can distribute this, I'm basically saying that I have 3 things that I want to drop down. And I just want to drop down those 3 things in a way where I don't put any more than one of them there. Oh, and that's giving me a way to check this 16. So I'm playing with combo here, right? So let's go back here. I want to double check the 16 with the same way of thinking. You see, I've got 4 spaces. 1, 2, 3, and 4. So I'm wondering how many ways can I put 3 things into the 4 spaces so that the last space gets no more than one of those things. That's actually what's going on here. Ah, now I can actually see how this happens. Because if I want to know, and the last spot either gets 0 or 1 thing here, that's actually what's going on. Getting the 0 things here, meaning like the 4, 5, and x all went there, I just need this number 10. This number 10 should come from the number of ways to grab 3 numbers that add together to make 3. That's really what's going on. I have 3 gaps here, and I want to put 3 things into them. Actually, is that right? How many ways can I put 3 things, like however many numbers are in here, however many numbers are in here, and however many numbers are in there? A plus B plus C equals to 3 would correspond to the 10. And the reason I say that is because it's like I've got the 4 and the 5 and the x, and I'm trying to drop them into these 3 cavities. And I just want to know that the sum is all 3 of the numbers are there. That's the blue kind. And the white kind is going to be a plus b plus c equals 2. Beautiful. Now it's not even bashy. So if I want to have the number of ways to make this plus this equals to 2, that would be like putting that last number, the 10, at the end. And by the way, if I want to know how many ways can I get 3 numbers which are non-negative integers, bigger or equal to 0, summing to 3, the way to do that is you go and say, I've got 3 things. And I've got 2 dividers, right? And I just want to know the stars and bars trick of how many ways can I rearrange these. If I saw this picture, that would be the 4, 5x. If I saw a picture like, I don't know, this, that would be a 4, leave this blank, 5 and x are both there. This is nice. So suddenly this works because 5 choose 2 is 10. And to get a sum of 2, that would be 4 choose 2. That's 6. Okay, now this is nice. We're getting the whole answer coming together. So now what I have is I have, back to this thing, that's why I was thinking of stars and bars. I have the 2 and the 7 I'm putting down. So what's really going on is I've got 2 numbers, that two things that I'm trying to put into some gaps. How many will I put there? How many will I put there? How many there? How many there? How many there? And how many there? Okay, so I have, yes, that's right. So I either have, if the 8 is among them, right? If the 8 is before the 9, then it's equal to the number of ways for a plus b plus c plus d plus e plus f is to be equal to 3. Because all three of the numbers, 2, 7, and 8, have somehow dropped in like rocks into this part. And the number of ways to do this is just the number of ways to say I've got 3 things, and how many separators between A and B, between B and C, between C and D, between D and E, between E and F. Is that right? I'm just going to count those things. It's like 1, 2, 3, 4, 5. Yes, 5. So now I have 8 to choose 3. That's the number of ways to make the 8 drop before the 9. Okay? So 8 choose 3, that's 8 times 7 times 6 divided by 3 factorial, which is, by the way, 6. That's 56. Okay? And that's cool. That's if the 8 is before the 9. Right. And by the way, this was this case where it's like, how many numbers? This 9 is at the end. Let's remember where that came from. That was where the 9 came at the end. There were 10 ways to do that. So there were 10 ways to get this. Okay? There were 10 ways to get this particular picture where I have all of these blocks before the 9. But there's another possibility. The 8 comes after the 9. Else, 8 is after the 9. So the number of ways is same as for A plus B plus all the way to F to be 2. Because now I need to have that the 2 and the 7 live here, and then the 8 lives at the end. Okay? Somebody asked, is this too hard for middle schoolers? Well, by the way, it could be that I have a really bad way of doing it. So maybe it's not too hard. But I'm actually just doing this I'm just doing this out because I'm just very curious what's going to happen. And while we're doing this, we're uncovering all kinds of neat combinatorics things, which is interesting to me. To me, actually getting an answer is not the only interesting thing. Learning about some patterns and learning about some things is also more interesting. And yes, there's probably a simpler way, which you guys will tell me at the end. But so what this is going to be equal to, same as this, which is now 2 dots and 5 bars, which is 7 choose 2, which is 7 times 6 over 2, which is 21. Okay? All right. So these are the two possibilities, 56 plus 21. If I add those two numbers together, that gives me 77. Oh, neat, 77. So over here, I have 77. Don't forget that's supposed to be times by a 10. Okay? So that's going to give me 770 so far. And the last part is to do the white ones. The last ones where there are 6 ways to have the white picture. And the white picture was like 9 and then an X. Okay, so 9 and then an X. So that means that there were 4 numbers before the 9 and then something and then a 10. So there were like 4 numbers and then a 9 and then there was the 10. Okay? And then now I'm supposed to go and put down the 2 and the 7 both to the left of the 1. Okay? So to the left of the 9, I'm supposed to put the 2 and the 7. Okay, so if I put the 2 and the 7 here, I can put an 8. Oh, the 8's either going to live here or it's going to live there. But the good thing is that, right, so that's just going to give me 2 choices at the end of how I put the 8. I'm just going to repeat the same thing we just did. So it's like if the 8 is before the 9, if 8 is before the 9, then just following the same thing we had from before. Now how many gaps do I have? I have actually 4 separators. That's what's here. Over here I had 5 separators. And now if I have the 8 before the 9, I need to put 2 dots into these 1, 2, 3, 4, 5 cavities, right? So then the number of ways is if I have 2 dots, 3 dots. If the 8 is before the 9, all 3 dots go there, and there's 4 separators, which is equal to 7 choose 3, which is 7 times 6 times 5 over 3 factorial, which is 35. Okay, that's if the 8's before the 9, else the 8's after the 9. Now, if the 8's after the 9, I've got two choices because the 8's either here or there. So I have 2 times, I'm just doing it faster, the number of ways to get, if the 8's after, I have 2 dots to separate, 2 dots to put in here with those 4 separators. 2 dots, 4 separators, which is 2 times 6, choose 2. That's just 6 times 5, because I would divide by 2 and then times by 2. So that's 30. Whew, that's 65. Okay, so my answer to the whole problem is going to be 770 plus 65 times 6. Is that right? Let's see. We'll find out. So 65 times 6 is what? Running out of space. So I have 65 times, yes, because this was like 6 ways and then here. So I have to do 65 times 6. 5 times 6 is 30. 6 times 6 is 36, I think. 390 plus the 770. So I have a 390 plus a 770. Where can I do that? Over here. 770 plus the 390. Okay, that's a 0. 7 and 9 is 16. 1160. Okay. Let's see if this is right. I don't know. Let's find out. 1160. Where's the answer? What? It works! Okay. Now, in that case, I'm pretty sure that wasn't the intended solution. It works. Cool. It works. And now, yeah. I mean, like, if it was wrong, it would just been like, oh, well, that's too bad. But, okay, why did I do this? I did this because I wanted to show you that there's, like, lots of interesting patterns. The heart of this... Wait, I got it wrong? No, it's right. It's right. Okay, so it's right. So the thing about this is, like, if you can see what I was doing, I was actually muddling around for a while looking for patterns. And then I suddenly was like, oh my gosh, it's related to stars and bars. So the reason I said it's related to stars and bars, it has something to do with like dropping 4s and 5s into places. Like there were these different buckets I was dropping things into. And the reason I had the foresight to notice that it's going to matter whether the 10 is after the 9 or before the 9 is because I sort of saw that this was going to happen. That if you're dropping things into these buckets, if the 9 is at the very end versus right before the end, the number of buckets you have is different. So now, oh yeah, sorry guys, I got really excited and yelled into the microphone. But now I'm a little bit curious. Somebody said there was a better way to do that? Okay, there might be a better way to do that. Obviously, this is what I came up with. But this particular problem is, as you saw, I tried to do something which was more fancy, but it didn't work. Well, at first I was like, not more fancy. I was like, I wonder if I can just like break it apart a piece at a time. And that's like painful. So instead what I saw was, oh, I see these chains of things which are parallel. Maybe that could help. The things that were parallel were these. There might be some much better way to do this. Perhaps the organizer will tell all of us. Do we dare to keep going? This was question 10. How do you guys solve these problems? Okay, let's keep going. But meanwhile, by the way, there is supposedly an easier way, right? Would someone like to just like mention what's the easier way? Fix 9 in each of the last 3 places you can separate the chains. Okay, so, all right, so that's sort of what actually ended up happening here, right? So what ended up happening here is we actually were basically looking at where 9 is going to sit. 9's either going to be 1 before the end, or at the end, or it ended up being 1 in the previous one. So if 9 gets fixed in the 8th, 9th, and 10th positions, okay. Nice. Okay, so what they're saying is that, look, 9 is in one of the last 3 positions. And that's what we saw from the thing that I did here too. So 9's going to live in one of the last 3 positions. Once you've dropped the 9 down, then you have this problem of like putting the 4, 5, the 3, 6, and the 2, 7 before it. Although I will say there's still like, it's still got some flavor of what's going on here in order to figure that out. I think that depending on how your brain works, that might indeed work very well. I also want to emphasize, I was doing this in a way where I was kind of like trying to discover it and show you how you discover it. Once you know that this works, the answer becomes much easier. You don't even have to make this list. Like once you know this works, you're like, once you know this method will go through, you can actually go and just count how many blues and how many whites straight up with like stars and bars. But in any case, let's go on to another question and see if we have something that might be a bit more understandable by more people, including me. Yeah, people said it took me 26 minutes to do that problem. You guys are just good, okay? I'm a bit slow. A function f is defined as f of ab equals 1 over a plus 2 over ab plus 3 over ab squared, and so on. Evaluate f of 16 and 15. You want to what? Oh no. Okay, wait. So I like to write things in ways that I can read it better. 1 over a plus 2 over ab plus 3 over ab squared plus forever. Oh boy, infinite sums for middle school students. This is pretty impressive, you guys. Right. So this is actually a fairly famous kind of problem. All right. Okay, so what we'll do here is, first of all, like, hey, check it out. There's a 1 over a everywhere. Let's take the 1 over a out. 1 over a times some stuff. What stuff? Well, it's 1 plus 2 over b plus 3 over b squared plus 4 over b cubed plus forever. That seems kind of nice. This actually is what some people call an arithmetic geometric series. Okay? So now there is a way to break this apart. The cleanest way to break this apart is to go 1 over a times. You know, it would be really nice if I just had like a bigger bracket. Wait, what? Yeah, that way. A big, huge bracket. Yeah. I want just like, you know, let's go 1 plus 1 over b plus 1 over b squared plus 1 over b cubed and forever. Wouldn't that be great? No, it's wrong because it's 2 over b. Oh yeah, okay. So let's add another. Let's use a different color here. Let's add another 1 over b plus 1 over b squared plus 1 over b cubed plus forever. See that? Now I got my 2 over b. How do I get 3 over b squared? Well, let's just do it again. Plus 1 over b squared plus 1 over b cubed, and go on. Do you see what this is doing? Each of these is nice. What's the next row? Now, why do I like this? Well, each of those rows is a geometric series. So that means that the whole sum is going to be equal to 1 over a times, what are all of these? So the first one is an infinite geometric series of the form, the first term over 1 minus the common ratio. Is that clear? That's this first thing. It's going to be the first term over 1 minus the common ratio, which is 1 over b. This is actually pretty good. The next thing, let's put a big bracket. The next thing is plus, oh, neat. So it's going to be the first term, which is a 1 over b over the same common ratio. I'm going to write it as 1 over b times 1 over 1 minus 1 over b. The next one is going to be the first term, which is 1 over b squared, divided by the common ratio, but I'll just write it like this. That's kind of neat, because what we just found out is like, that's a geometric series too, isn't it? Because I have the same first term, and I have this like 1 over b squared, 1 over b cubed, and so on. So that means that the whole thing is equal to 1 over a times 1 over 1 minus 1 over b. And then like, it's going to be again. Did that make sense to people? Because this is like this is the first term, and the common ratio is 1 over b. So it's the same thing again. So now I just need to know what happens when I plug in a equals 16 and b equals 15. Maybe let's simplify this a little first. This is 1 over a times. Now multiply top and bottom by b. So it becomes b over b minus 1, whole thing squared. I don't understand how middle school students know this much, but you guys are just very impressive nowadays. So that's the answer, right? I just need to put this, I multiply top and bottom by b, so it's b over b minus 1. And so now what I have to do is I just have to go and plug in A equals 16 and B equals 15, right? So if I plug in A equals 16, B equals 15, I get 1 over 16 times 15 over 14 squared. Yuck. What kind of a crazy fraction is this? Did I make a mistake? I don't like this fraction. Seems legit. I guess, but then I need to go do some crazy multiplications because there's no canceling. Because 15 has no common factors with 16 or 14. That's because 15 is only differing by 1 from each of them. Okay, so let's go and try this. Yuck. I know 15 squared, that's 225, okay? But what I don't know is 16 times 14 squared. I know 14 squared. 14 squared is 196. And then multiply that by 16. I guess I could do that. 6 times 6 is 36. 6 times 9 is 54. Okay. 6 times, do I believe that? 6 times 9 is 54. Yeah. 6 times 1 is 6. 1176 so far. Okay. And then the 196. Add 6. 7 and 6 is 13. Okay. That gives me 1 and 9 is 10. That's 11. 3136. All right. Hello, 3136. 225 over 3136. Let's see if this is correct. 225 over 3136. Yes, okay, that's right. Now this time I didn't blow out the microphone. But the reason is because this is like fairly algebraic. I probably didn't count wrong. Okay, I probably didn't count wrong. With the combinatorics things, you never know if you just like forgot a case. Well, we got some time left. Let's keep going. We got like 14 minutes left. Question 32. Consider the toy below constructed by placing two regular pyramids above and below a cube. A trainer paints each face of the toy with one of the colors black, gold, green, and white, such that the faces completely opposite, parallel to each other, are painted the same color. What is the number of unique ways that she can paint it so that no two adjacent faces, which share an edge, share the same color? Note that two ways are not considered unique if they can be rotated to... Oh my gosh. How are you supposed to solve these problems? Okay. That's going to be hard. Two ways are not considered unique if you can rotate them to look like each other. So each of the faces gets one of those colors so that they're opposite. So first I'm counting up the number of faces. So it's like I've got 4 faces on top, 4 around there, and 4 on the bottom there. So I've got 12 faces. And what are my colors? How many colors? 1, 2, 3, 4. Got 4 colors. Oh boy. Okay. Aha. Oh, somebody just gave me an advice. The advice was take a look at the next one maybe, because there are some other ones which are maybe better to do. So what I'm going to say is like, I'll tell you why this got me scared. It's because whenever you have to do these things with these rotations, there's like a lot of cases of like, you can rotate it like one tip or you can rotate it 2 things and make it look the same. Let's go with another one, okay? Yeah, because the problem here is there's 4 colors and there's like 6 pairs of parallel faces. So it's going to be a very, you got to be careful on this particular question. Let's see if we can find one that might give some kind of a mathematical, I'm not looking at the answer, some kind of like a little bit more like systematic or structural solution. Let's try this one. Yeah, there are lots of rotations. The problem with the previous one is that there are different kinds of rotations. Some rotations when you just turn 90 degrees is one kind, but turning 180 degrees is another kind. So doing it very carefully is hard. All right, mounting mayhem number 3. The 4 symbols below each represent a different integer value. Oh, yes, there are symbols. And there's 4 of them. Okay, I see that. Is that right? Wait, how come I only see 3 horseshoes? Oh, that's because there's 5 horses. Mustangs. Okay, good. Right. Given the numbers on the right represent the sum of each row, and the numbers on the bottom represent the sum of each column, determine the sum of the second column. Okay, so these are all different integer values, huh? So at first I was like, gee, I wonder if there's something nice of, it's like, I can just say like there's 4 of each thing, but there aren't 4 of each thing. There's like 4 of these logos, and there's 4 saddles. Well, let's start to go and look at any kinds of patterns that I can find between things. Meaning, I can, for example, find the, I see. I was going to say, I could find the difference between a Mustang and a saddle by knowing something about the difference between these numbers, but one of them is the unknown. So what that's telling me is if I could find the difference between a Mustang and a saddle, let's give some names. Do they all have different names? Yeah, they do. Okay, so here are the names. This is officially called a horseshoe now. That's a horseshoe. We have a saddle, which is not a 5. We have a logo, and we have a Mustang. Good thing we're not calling it a horse. Okay, so we got all of these things. And what I'm seeing here is that the gap between these two, if I want to go from this one to that one, what I have to do is I have to plus a saddle minus a Mustang. Yes. So if I knew something about the difference between saddles and Mustangs, I'd be in good shape. All right? So now what else do I have? Oh my gosh. Somebody here just told me I'm an idiot. Okay, so I'm sorry. I saw the chat. You guys are too good. So I was going to try to find some relation between, like what the difference is between things. But because somebody just pointed out that, the sum of everything is the sum of those numbers. And so that better be the same as the sum of all those things. So that finishes this one. So I'm going to say you guys would have beaten me to this. Good for you. Yes, I can do a little bit of arithmetic and we can figure it out. Let's go and do that. And let's go to the next problem. But yes, this is indeed a very beautiful question. And good job, guys, for finding something that's way, way better. I was like looking at little things. But yes, totally. The sum of all of these things is going to be the sum of the whole table. So if I only knew what was that sum, that'd be great. What is that? Let's write it bigger. So if I had 31, 46, 52, and 47. All right. 6 plus 1 is 7. That's 7 plus 2 is 9. 9 plus 7 is 16. All right. And I have 1 and 3 and 4. Okay, 1 and 3 is 4. Plus another 4 is 8. Plus a 5 is 13. Plus a 4 is 17. Hopefully I can do arithmetic. Double checking looks right. Actually, you know how I double checked that? I saw 3, 4, 5, and 4 average out to 4. So that should be 4 times 4 plus a 1. That's 17. On the other side, I know how to add these. 40 and 50 is 90. And add a 48 is 138. So I just need to know 176 minus 138. Oh, so nice. 16 minus 8 is... 16 minus 8 is 8, and then 6 minus 3 is 3. 38, guys! I think the answer is 38. Okay, let's see if that's right. All right, good job, guys. Guys and girls, good job for all of you who did this. I was too slow. Do we have some time? We've got 7 minutes. By the way, organizers, if you have an idea of a better one for me to do, let me know. Otherwise, I'll just focus on this one. Good job for all you guys who got that one. Maybe one more. We'll do one more. But the question is, should I do this one or should I do the next one? Or is there a next one? Let me know which one you think. Organizers haven't said anything. So I would take a look at a different one they said. Okay, let's see what else we got here. Okay. Got some parallel lines. Oh, cool. That sounds kind of cool. What's this? F of g of 2 is 7. G of f of 2 is 8. Yeah, this one's better. Let's try this. And f of 2 minus g of 2 is a half. Neat. So these are parallel lines. Okay, so if I've got some parallel lines here, well, is there a clever way I can do this? So these are parallel lines, and also f of 2 minus g of 2 is 1 half. I like this, okay? So I know that I've got some like f of x is equal to the slope, mx plus b to me looks like 6. So I'm going to do mx plus a, all right? So I've got like some, you know what? I'm going to call it ax plus b. Ax plus, my whole goal was to avoid a b because it looked like a 6, but I guess it's back. All right, so I've got ax plus b is f of x. Oh, but by the way, g of 2 is just a half less. Yeah, g of 2 is equal to f of 2 minus a half. So that means that g of x is equal to ax plus b minus a half. Did that make sense to people? That's actually how I will always get f minus g to be 1/2. And if I plugged in a 2, that happens there. All right. So in that case, I could actually go and try to solve this, right? Like I'm a little bit curious if there's a nicer way. Just looking at this. Maybe there is, maybe there isn't. But like I would be able to do something with this. Because if I want to know f of g of 2, oh yeah, let's go plug in some 2s. That'll make life... okay, let's see. So if I wanted to actually do this, what is f of g? Let's find out what f of g is. So if I want to know f of g of x, that's going to be, you just put a g in there, ax plus b. I want to see if there's a neat pattern. Minus a half, okay, and then plus a b. That's f and then g x, right? So sorry, no, that's g first and then f. That's f of g of x means you do g first, throw it in there. That's kind of interesting. Well, what happens if I compare that to g of f of x? G of f of x is going to be a times ax plus b, and then minus a half. Oh, interesting. So now between these, I can figure out what the difference is. You see, because the difference between these two things, they look almost the same, except that this guy has a over 2, and this guy has 1 over 2, and everything else is the same. So if I want to know what happens if I subtracted them, for example, this is neat. You guys are really creative with making questions. F of g of x minus g of f of x. That just so happens to be, if I subtract this way, that's negative a over 2, and then plus a 1/2. Do you see how I did that? I was just like, there's so many terms in common. Like that part and that part will cancel each other. The b and the b will cancel each other. So this is great because I know what this is. I know what this is when I plug in a 2, for example. When I plug in a 2, I get 7 minus 8. So that means it's negative 1. At x equals 2, I get negative 1 is equal to minus a over 2 plus a half. Okay, so if I subtract a half from both sides, subtract a half, so I get minus 3 over 2 is equal to minus a over 2. So that tells me that a, which is the slope, is 3. All right, let's see if this is correct. It is, and we're good. Okay, so that actually finishes this question. It is a very nice question. You guys have pretty good problems here. They're very interesting. We have like less than 3 minutes left, so I'm just going to do the rest with just like any random questions, because as we know, these questions are pretty creative, and some of them are quite involved. Any random questions that you want me to answer, or random stuff? If you want to ask math questions, come next week. I haven't asked math anything. How about other like random questions? Can you do? So somebody is saying do one more problem. We can do that. So is that the case? Is that because I saw Mustang Math Tournament say do one more problem? Relay number 1. Is there a relay number 1 here? Is that what you want? Or Gallup 23? So let's ask Mustang guys. What do you want? Is relay 1 in my list? Because I don't know actually, I have no idea what's in this list. So I just need to ask the organizers, should I do this one or should I go forward? I'm watching the chat to see if the organizers have given some suggestions. Relay 1 is not. So relay 1's not in this list. So in that case, what should I do? Gallup 23 perhaps. Okay, so I'm going to move forward. Gallup 23, galloping time. Gallop, 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 gallop. I don't see a 23. Wow, you guys gave me a lot of problems. Okay, what's this? Okay, Minty Mustang just bought a cone of mint ice cream. As shown in the left diagram below, the spherical ice cream scoop sits within a right circular cone with diameter and slant height equal to the diameter of the sphere. Diameter and slant height are both equal to the diameter of the sphere. Okay. Neat. Unfortunately for Minty, it's a hot summer day, and their ice cream has begun to melt. After some time, exactly enough ice cream has melted so that the bottom of the scoop reaches the level of the melted ice cream. Okay. And that's right. If R is the ratio of the melted ice cream height to the height of the cone, find R to the 6th power. Wow. Okay, so we have a spherical ice cream scoop. And we know that the diameter and the slant height are the same. Okay. Wow. Okay, I'm gonna say this one's gonna be something which is a bit more calculational. So I'm gonna say this one can be done. I know this thing can be done. I also know that we're running over time, so I'm not sure that we'd be able to do this one in just a few minutes anyway. But Gallup 15 is a short one. Did I pass Gallup 15? Have I passed Gallup 15 yet? Or is it ahead? I have passed Gallup 15? Gallup 15 is short. Okay, so I'm going to like cover on my side so I can't see the answers. I'm galloping backwards now. Okay, now we're going forward. So I wasn't looking at the answers. All right, let's just do this. Just because I want to be careful, we are over time and some people are probably going to sleep. And by the way, the previous one is like, yes, it can be done. It's just like a bunch of like triangles and angles and so on, but that might take a while. So, okay, regular hexagon with a point P contained inside it. What's the probability that P is closer to a vertex of the hexagon than its center? Okay, so, right, regular hexagon. How to get closer to a vertex than its center. So the way this works is that I'll have like, this is like a post office problem or a Voronoi diagram. So what I'll be doing here is I'll be drawing the boundaries at which we're sort of breaking the tie. Well, that's where there's a tie between this. These are the points which are same distance from the center and that vertex of the hexagon. But as I draw all these boundaries, this thing here, by the way, is the perpendicular bisector of the line segment with this point and that point, right? That's how I'm drawing these things. This is a really nice idea. This is a nice problem. Like these are all of the splitters. Do you see what I'm doing? And actually, if you are curious, this is also related to the ideal way to run in football. I have a YouTube video on that, one of the first things that I made about on YouTube. But anyway, so like this is like created by drawing all of these split lines. And so I now need to know what's the probability that I'm inside here, or that I'm not inside here. Inside here is the thing that's closer to the center of the hexagon. And instead, like, I want to know what's outside here, because that's closer to some vertex, right? Because this is like, if I went and drew all the boundaries of here's how you get closer to this point than each of the vertices, I'm there. Now, if I want to know this ratio of areas, let me just do the ratio of the area of the inside to the outside. Sorry, the inside to the whole thing, and then we'll take 1 minus that, right? If I want to do that, all that really matters is to figure out what is the ratio of, what's the easiest way to explain this to people? Yeah, what's the ratio of this thing to, let's use another color, to this thing? Whoa, that's really, really bad drawing. Because let me just draw it this way, to this thing. Because what I'm saying is that, you know, like that's one of these things that determines the half of the height of the hexagon, and this is the half of the height of the other hexagon. So it'd be great if I could compare those two, but you can't. The way that you can is that you can take, for example, this one and run it through this way. Okay? Happens to be the same, or maybe I'll draw it like this. Here's another way to see this. That's also this piece here, but that keeps going here. You see that? And this is a 30, 60, 90 right triangle. So if I have a 30, 60, 90 right triangle, let's just write down some things. Suppose this was 1, and suppose this whole piece was root 3, and then each of these would be 1. Because this would be a 2, 1, root 3 situation. So now what I just found out is that the ratio is 1 is to root 3. That means that the area of this thing is 1/3 of the area of the whole thing. So the answer is 2/3. Hopefully this is right. So this is just like, like I just used the 30, 60, 90s, and then that's like the 1, that's the root 3. So the ratio of areas is equal to 1 over root 3 squared, which is 1/3. But we care about the complement. So we do 1 minus 1 over 3 is 2 over 3. And we hope that that's the right answer. Yes, it is. Okay, and with that, we have finished today's live stream. I enjoyed talking to all of you. These were some pretty challenging questions. And congratulations to the organizers for putting this all on. I'll see you all next time. Take care. Bye-bye.